Thank you. Well, it really does look like a great conference, and I'm really honored to be asked to chair here. I'm not really an expert on this field, but I guess authors told me in no uncertain terms that my most important duty is to make sure people are on time, and so maybe I'm good at that, and I will do my best. You have 35 minutes with questions, but it better be over, but you better leave time for questions, and I will raise my hand when time comes. And this is Mikhail Lukin, whom I think needs no introduction, or introduce in some sense.
Thank you. So let me see if I can handle this. So I would like to start by thanking Arthur for his incredible leadership, and in particular, many of you know that one of the things after this program started, it was a mathematical picture language seminar, which was just one of the other talks which were taking place at Harvard. But I would say when pandemic started, this seminar really transformed into something which is really a very special worldwide phenomenon. So, and many of you have participated in this every Tuesday morning, Boston time, evening, Beijing time, kind of people from all over the world. So, joining, and it's been, I've participated in a couple of these events, and it has been really truly incredible experience. So in keeping with what Arthur has said previously, at Harvard every rule has exceptions. So this conference is largely a mathematical conference, or theoretical at least. And so this rule has one exception, and this is an experimental talk, which I'm happy to present. And so what I would like to do is tell you about a little bit our effort, which is part of the quest for controlling quantum all. Namely, it's an effort to build actual, working quantum machine. And in this effort, what we do is we start from isolating and controlling simple quantum objects, and then building more and more complex systems from them. And what we hope to do with the systems is really study new physics and kind of explore, create and probe new entangled states of matter, but also start exploring applications such as quantum information processing. And while you hear about this field, I would say now almost every day, it's important to sometimes step back and kind of think where we are. So this field faces two big challenges. So one challenge is how to build truly large-scale quantum systems. So the answer, if and how this can be done, is right now not known. And by that I mean systems containing millions of, good or near perfect qubits. And what's perhaps even more striking is that, even if I were to kind of bring, one of the systems here, okay, maybe this is an exception, but in general, people wouldn't really not know what to do with that. So if I were to give it to you, I mean, I'm sure there are some people have some very good ideas, but there are very few of these ideas. And basically, what these quantum machines can do is really something that the question, which is also a big question, which is we have to answer. So with all that said, I would say it's a special time in this field, because we are building now machines which are big enough, quantum enough, programmable enough that we can really use them as tools for scientific explorations. And this is something that I hope will actually be of interest for your community, in fact, inspire new collaboration. So here is what I'm planning to do today. I'd like to tell you a little bit about, how we in our lab build these scalable quantum systems, and we do it literally atom by atom, assembling quantum matter and quantum controlled quantum systems. And then I will tell you a little bit what one can use these systems for. So I will tell you about creating and probing quantum phases and phase transitions in 2 dimensions, about experiments to create topological matter, such as, for example, topological spin liquids, and also how one can use them to try to accelerate quantum optimization. And then hopefully I have a little bit of time for an outlook, basically, tell you a little bit where this, where this research is going. So as I already mentioned, in our lab, we built this quantum system from single atom, literally atom by atom. So what we do is we start with a gas of atoms in a vacuum chamber with very low density gas. And these atoms are slowed by shining laser light on them. They're slowed down by using the so-called laser cooling and techniques. And then what we do is we basically shine into this chamber focus beams of light, like the one shown here, and we focus some SOTA, and these focus beams attract the atoms to the point of the maximal intensity. So in a sense, they act like optical tweezers, basically, these atom traps, which can hold the light, hold the atoms in a vacuum for a long time. And we focus these light beams very tightly, such that each of these tweezers holds at most 1 atom. So but what we do, typically we don't just start with 1 tweezer at a time. We start with by now thousands of these tweezers, and then try to load them. And what happened in this case is that the system has an entropy. So we end up with some traps which are loaded and traps which are not. So the system has a lot of disorder, has a lot of entropy. So to get rid of this entropy, what we literally do is we take a picture of the atoms, figure out which traps are loaded and which are empty, and then remove the empty trap and rearrange the desired atom, the rest of the atoms in the desired configuration. So with that, we end up with atoms which are tightly localized, spaced by about 2 microns, so that we can actually, or more, such that we can take pictures of these atoms. But at this point, the atoms do not talk to each other. They cannot tunnel, they do not interact. So they are completely classical objects. So to induce interaction, what we do, we excite these atoms into Rydberg states, and so states with a large principal quantum number, and that allows us to execute quantum logic engineer interaction. And this is our joint project within Harvard MIT Center for Untitled Atoms with my colleague at Harvard, Marcus Greiner, and our colleague at MIT, Adam Wood. So let me just talk a little bit more about how we engineer the interaction. So we like Rydberg states because they combine long lifetimes. They live for typically hundreds of microseconds and strong interaction. So the interaction scales as 11th number of this principal quantum number n. And for example, for n equals 100, it's 14 orders of magnitude. The van der Waal interaction is 14 orders of magnitude stronger than the van der Waal interactions between the atoms in the ground state. So this 14 orders of magnitude is a large number, and it's not infinity, but this is something we can make a good use of. So a specific mechanism which we like to use it for is something which is called Rydberg blockade. It can be understood as follows. So suppose you drive the atoms resonantly, and they are far away, they would just undergo independent Rabi oscillations. But when you bring them close, eventually this strong interaction will take over, and these interactions will actually shift the doubly excited states and all other states, far from resonance. So what will happen is that if you basically still trying to excite the atoms resonantly, is that you will be able to excite at this point 1 atoms, but never more than 1. And that's the idea of this Rydberg blockade, that simultaneous excitation of atoms is blocked at distances smaller than RB. And it allows us to entangle atoms, execute quantum logic in a very robust way, because at this point, this mechanism is insensitive to exact motion, position of the atoms. So, and actually as a result, it's very robust. So in sum, what we'll do is we'll prepare, some kind of artificial crystals of atoms. And then, subject these atoms to sequences of pulses, which will induce interactions, we'll execute quantum logic, and then we'll just, read out the state of the atoms at the end of the operation. So this approach can be used for multiple different modalities. It can be used as digital quantum processor or kind of analog. But one actually interesting kind of modality, which we very much like to use, follows the original idea of Feynman, of this idea of programmable quantum simulators. So, and it literally is actually implementation of some, like some of the things that he wrote about. So basically, as an example, we can consider the chain of atoms, which are equally distant spaced. And so at this point, you can just think about this system as a spin system, systems of spins, which is described by this Hamiltonian. So this is kind of a Rabi flipping term. This is a term which is proportional to the detuning. You can think about it's a chemical potential. So N is number of Rydberg atoms on each lattice site, and the interactions. And so to get you a little bit, give you a feeling of what type of phenomena one could study with that, what we could do is look at a ground phase diagram of this Hamiltonian. So it can be parameterized by these two parameters. One is the tuning, and another one is the interaction range. And so if you neglect the interactions, then everything will be determined by the detuning. So basically, if detuning is negative, then you prefer all n's to be 0, right? All atoms should be in a ground state. If the tuning is positive, all atoms should be excited. But a state like this is clearly incompatible with this idea of blockade, which I just talked about. So for example, if just nearest neighbor is blockaded, so then you will not be able to excite this state, but at most you will be able to excite 1/2 of the atoms. And it's actually, they should be ordered such that every other atom is excited. So that's the state shown here. So it breaks Z2 symmetry. If you now increase the range of blockade, then you will also block not just the first one, but the second one. So it's, the state becomes up, down, up, down, up, so it actually breaks the free symmetry. And then this kind of situation continues. So we can explore such a phase diagram very easily on our machine by initializing all atoms in the ground state, adjusting the Rydberg blockade appropriately, and then just trying to basically adiabatically change the detuning to enter all of the states. And so here are some of our very first results, now a few years old already. So where in this case, we basically have a chain of 13 atoms, and they change this detuning, and we stop at various values of detuning. And then what you see is that, if you kind of change detuning from negative to positive, you end up with the state, which has this up, down, up, down, up, down. So this is basically a antiferromagnetic state. And we can really see a picture of that in real space. And then basically, if you now start, for example, change the blockade range, and here we do it by just bringing atoms a little bit closer together, such that not only the first, but also the second atom is blockaded, you now create this state with the free symmetry broken and with the C4 symmetry broken, etc. So what we see is that by just program the interactions, we can really create kind of a state here which breaks desired symmetry. So we are right now operating, and for the last 2 years, we have been operating what we call generation 2 of atom array experiments, in which we can create large-scale two-dimensional arrays containing up to about 300 atoms. We can prepare all sorts of artificial crystals, as shown here, different lattices, but we can also prepare some disordered systems. So, for example, here is the example of the pattern we would like to create. And you press a button. So here is the underlying atomic pattern. And as I said already, we start typically with about 600 traps, which are filled with something like 55–60%, and so basically it results up to about 300 sorted atoms. Each of them, each trap being filled with probability, more than 99%. So what we can do with this kind of systems, we can. Actually, one last thing is, of course, a tribute to sort of what happened over the last 2 years. So this is a kind of a remarkable day in our lab. So that's a day where we had to actually shut down all of the experiments. So, but thanks to Chris, who already has left, so we had precisely 1 week warning, and this actually 1 week was enough to convert this experiment to fully remote operation. So this work never stopped, and as you see, these people are actually kind of very happy, also exhausted. That actually means already people are running this, the machine from Zoom. So it has been in many respects a remarkable time. So just one example. So let's just see how this how we can look at quantum phase transitions in two dimensions. So here what we'll do is we'll assemble a two-dimensional system, adjust blockade in this case such that nearest neighbor is only locked, and then we just sweep the tuning, and then once in a while we see this picture. So this is a 2D antiferromagnetic, perfectly ordered across the entire array. This is not what we see on every shot. So in some shots we see defects, and we have all access to all of these individual images. So we can, for example, look at density correlation function, and this pattern really looks like antiferromagnetic. It actually looks like a checkerboard. So for this reason we call this phase a checkerboard phase. But we also can look at these images microscopically. Here is, for example, statistics of all micro states, and in fact, what you see here, that this state and the state which kind of complementary ordering basically are the most probable states. We can look, what probability these states occur, and what's actually maybe even more interesting is we can look at dynamics, how this correlation grows. So by going through transition with different speeds, we can explore, how these, correlations emerge. And in fact, we can use this information to extract things like critical components by using the fact that these phase transitions should be universal, close to the critical point, behavior should be universal. By kind of rescaling all of these curves with proper critical exponents, we can really extract them. This actually, by that, we can, for example, observe and study these, quantum phase transitions. In this case, it's an Ising quantum phase transition in 2+1 dimension. So apparently, up to now, it has not. They have been studied theoretically with a textbook result, but they have not been observed up to now. So, okay, with all of these tools, it is kind of a special time in our lab, and over the last 2 years, we have enjoyed a wide variety of remarkable kind of explorations. So we studied more exotic phases in 2 dimensions. We studied non-equilibrium dynamics by basically pushing the system in the corners of Hilbert space where no one has ever been. We kind of always discover something. And this is something, for example, quantum many-body stars we will explore. So I will tell you a little bit about our explorations of topological matter, attempts to accelerate combinatorial optimization, and this is the last kind of special topic I would like to describe. I would also like to mention that we now have 2 machines in town of the kind that I described. So across the river, our startup company, Quara Computing, aims to actually kind of deliver this machine as a kind of cloud service so that everyone, including theorists, can log in and play with it. And I think this will happen in the next couple of months. Okay. So with that, what I'd like to do is talk a little bit about some of our recent work aimed at probing something which is called topological spin liquids. So topological spin liquids, as most of you know, is a special form of matter which was postulated by P.W. Anderson to emerge in some systems which have frustrations, so-called frustration. So frustration is where basically the system cannot order in a kind of nice state like the one that I showed here. And this was initially kind of considered to be kind of very wild idea, because sort of the idea was that the system's property will be encoded in systems topology. But over the last 50 years or so, it kind of really emerged as a very exciting frontier in condensed matter research. So this matter is expected to have some exotic properties. So it should have something which is called topological order, right, which is robust against perturbation, long-range entanglement, emergent gauge theory, ionic excitation, and has been really a major effort for the past several decades. And about 20 years, this field was given another boost by Alexei Kitaev, who pointed out that these kind of states can be used to build topological qubits, where quantum information is encoded in topology, and as such, it can be robust. But despite these remarkable efforts, basically up to now, there is no conclusive experimental evidence in any kind of real-world system of such states being present. And kind of early in the pandemic, we were actually very excited where, 2 of our colleagues, Subir Sajdev and Ashwin Vishwa, our group, who pointed out that we can use our system by using this idea of Rydberg blockade on frustrated lattice to create such things. So the idea is of the following. So let's consider this kind of rather exotic atom arrangement shown here, where atoms live on the links of the so-called Caganel lattice. And let's arrange for the Rydberg blockade such that for one atom on one of these links, 6 of its nearest neighbors are excited. So, so clearly you cannot excite all of the atoms here. So in fact, at most you can excite 1/4. But actually, it turns out that the nicer way to think about the system is by mapping it into something which is called a dimer model. So basically, in this case, this blockade ensures that, for example, if we draw this atom as a kind of dimer which touches both vertices here. So due to this blockade, no dimer can touch more than basically no dimer can touch 2 vertices. So basically, that's kind of what's called dimer covering in this language. And there are many more of those. And actually, what Subir and in particular Ashwin and his postdoc Ruben Warsin pointed out is that under certain conditions, this system should be a superposition of all of this kind of dimer cover. So the system has actually should have a Z2 topological order. It's actually basically equivalent to something which is called resonating valence bond state, also a very famous kind of theoretical prediction. Okay, can we study these things and how? So one way is we can just create this arrangement that I've shown here in our lab and try to do this adiabatic evolution and just take a picture of atoms, and you see that this indeed kind of looks like a dimer covering, maybe not perfect, there are some errors here and there, but it's really very hard to say if the system is ordered or not, because if you repeat this experiment, you get basically another of these dimer coverings. So how can we quantify this topological order? So one way of doing it is to really study topological string operators. So they are basically observables in toric code. They are products of X operators and Z operators on dual lattices. And actually, in our case, it's relatively easy. At least the Z strings are relatively easy to understand. So suppose you draw the string which goes around one vertex, and if you have a perfect dimer covering, it should really cross just one dimer or one Rydberg atom. So the parity expectation value of all of these strings should be -1. So if you draw the bigger string, then the expectation value should be -1 to the power of the number of enclosed vertices. And this is something which we can easily measure. We can just, draw one of these loops here and just, look how many of the excited Rydberg atoms or dimers it covers. And indeed, what we see is we now kind of adiabatically move into this state. We see that, somewhere around 1/4 filling, we see it's a little bit of a kink. So it's not really a plateau, but, it's a kind of something is happening here. And indeed, what we see is that these string operators acquire the expectation value, which actually behaves correctly with respect to this kind of expected law. So what we see is that this expectation value of strings decay as we grow a larger and larger loop. But even for the loop which is comparable to the system size, we see non-zero expectation. So this corresponds to basically transitions into at least approximate dimer phase. But of course, from these measurements, you cannot say whether you can create a superposition of all of this phase or just statistical mixture. So to probe that, we need to have another string operator, which will be off diagonal. So, and one way to define it is basically with the operator acting on the edge of each triangle, and what this operator will do will basically flip around all kind of combination of dimers like it's shown here. So you would say, well, it's very non-intuitive, why this is actually an X operator. So, but the nice property of this operator is that if you draw the closed string, then this operator takes one dimer covering and basically maps it to another dimer cover. And at this point, it starts to resemble a little bit the kind of analogy with qubit. Qubit basically takes 0 and puts in 1 and the X operator and takes 1 and then 0, and basically measuring this non-zero expectation value measures really coherence between 0 and 1. Likewise, measuring closed string here measures coherence between all of these dimer counters. So it turns out we can measure this. I'm not going to describe in details how this is done, but kind of to make a long story short, we observe also the non-zero expectation values of these X strings on the scales, which are basically comparable to the system size, which indicates that there is actual coherence present between these different dimer states. Okay, now how can we actually conclusively say if we are studying topological phase or something else? In order to do that, we have to define some observable which will care about systems topology. And in our case, what we can do is we compare closed loops and open strings. And this here is how we actually convinced ourselves that we are looking at something real. So here is the result probing the expectation value of closed loops, which has non-zero signal, and equally long open strings, which in this case is exactly, this just signal is that zero. And the same thing happens in some parameter regime also for the X loops. So one can actually formalize this consideration basically by defining the parameter, sometimes called BFFM or FM, string order parameter from lattice gauge theory, which is basically the ratio of open loops to closed strings. And actually it turns out it can distinguish trivial phase from quantum spin liquid from other states like valence bond solid. And indeed, we find that there is a parameter regime that this kind of expectation value behaves properly, and is from that we can conclude that we really see an onset of quantum spin. I of course have mentioned that that kind of application to qubits is, the kind of one of the motivations to drive this research, and we could not stop ourselves from making kind of a baby qubit. And so in order to do it, we have to create a system with non-trivial topology. So here what we did is we basically removed a few atoms, creating kind of an inner boundary of the system. And actually, that's kind of similar to this, famous example of the donut and coffee cup. And basically here, now one can define the topological operators, which are non-commuting. For example, X operator going around the inner boundary, and Z string, which goes from inner to the outer boundary. And it turns out in this case, basically the ground state should be doubly degenerate. So there are two superposition states which one can prepare. And actually one of them is what we expect to obtain an adiabatic preparation. And when we do this experiment, we indeed find that there is a parameter region where, this X string, around the this call is non-zero, and all of the other operators, kind of Z operators, obey the expected commutation relation. So it's really a first step towards the topological. So we are quite excited about these new results because they really offer unprecedented insights into topological matter. So it's a kind of a new tool which we have complementary to analytical theories and numerical simulations. We are looking now at no-analyze methods to analyze this, which are basically inspired by quantum error correction, and also to simulate. So this is an example of lattice gauge theory and Z2 lattice gauge theory. We are looking also at other examples now. And at the end, we hope that these experiments will give us some insights to engineer topological matter in real world materials, but also kind of use it as a platform for exploring fault tolerant quantum information processing. So here is a picture from the physics today, where I think the artist, I probably decided that these physicists and mathematicians completely have gone crazy, doing this kind of knots and braidings and so on. But these are the things we can now do in our lab by just using laser beams to create anyons and move them around. So I'd like to shift gears now, and actually I think I have maybe 5 minutes or so. Yes, so maybe I will skip combinatorial optimization. So in order to, since Arthur insisted we should do on time, and give you a little bit of a preview into kind of as an outlook into what we are doing right now. So up to now, what I have shown you is we have in our experiments, we assembled the matter and then turn on quantum evolution and just look what will happen. So, but what if we can actually interrupt our quantum evolution, store quantum information, and then rearrange the atoms, change the connectivity, and then proceed with the quantum evolution. So it turns out that it's actually possible to do it. In order to do it, you need to store quantum information in long-lived state, like spin state, which has long coherence time, seconds, and just use the Rydberg atoms to execute, for example, quantum logic. Just only when you need the atoms to interact, you excite the atoms into this Rydberg state. So let's see if this works. So this is an example in which we start with atoms nearby, we entangle them, create bell pairs, and then move the atoms far away, and then basically take again analyze the state. And what you see here, we basically move them across the entire array, and the coherence and entanglement was completely preserved. So kind of inspired that, we started thinking about a new architecture where we basically kind of dynamically change basically the architecture itself as a living organism. So as you do your quantum operations, you change its connectivity, you change how it works. So let's give just a few simple examples. One simple example is creation of the cluster state. It's a relatively simple state, but in this case, you basically can do it in two steps. One step, you start with pairs of atoms, execute control phase operation, then move the atoms, and then do another control phase operation, and then move atoms again, and then just measure, for example, in different phases. Here you can measure all stabilizers of this cluster state. So can we do something which is a little bit more complex? And in the spirit of what I just talked to you about, so let's talk about toric code. But in this case, what I'd like to do, I'd like to create toric code state on a torus. So toric code state, as most of you know, is an example of quantum error correction code. So here, a grid of physical qubits encode logical qubits, and they should be a building block for fault-tolerant quantum computing. And basically, the key idea to do that is to make stabilizer measurements using these ancilla qubits. So these ancilla qubits, these red qubits here, can be used to detect local errors. But actually doing that seems to be really quite hard, on the torus, because we don't really have kind of an access to such a geometry. But actually it turns out that this state is equivalent to the graph state with non-local connectivity. So this is this representation of the toric code, where basically this ancilla should talk not just to its nearest neighbors here and here, but also talk to to something on the other side. And likewise, this ancilla should talk to these three guys and talk to another qubit. So actually we implement this kind of toric code on a torus by using the idea which was originally suggested by Peter Zoller and Ignacio Chirac, almost 20 years ago, actually more than 20 years ago. This was a time when magnetic hard drives was still used. And so people, were used to this idea of this magnetic head, which would read, a memory. And they suggested that maybe instead of this magnetic head, one can use a qubit as a kind of quantum head. So basically, this idea was kind of at the time, was, considered crazy enough that people said it will never be implemented. So we implemented it now, but instead of one qubit, we now use 8 ancillas, which we can move around in parallel. And so here is the movie showing how we can actually make this kind of toric code on a torus. These ancillas move and they execute this controlled phase operation, and then we move them to readout zone to basically read them out. And so basically, in this case, we can encode 2 logical qubits, one going this way and another going this way. And actually, indeed, we can measure this expectation value. It should be both should be in X state, and you see that there are basically non-zero expectation value for all of these products of strings going this way and this way. This is not perfect, but now we have access to all stabilizers. So we can do, in this case, error correction or error detection. And one of those, basically corrects to 1, another one corrects substantially, but not quite to 1. But this is what we can do. So Again, this actually is very exciting time because we now have an opportunity to study all sorts of codes, hypergraph, LDPC. We are starting to look at hardware efficient way to implement error correction and also look for new approaches to combine analog and digital. So with that, I think I'm out of time. So thank you very much for your attention. I would like to also thank, people whose blood and sweat resulted in this. Thank you very much.
Thank you. Wonderful talk. I guess we have just a couple of minutes for questions, a little bit over.
Yes. What kind of 3D?
Yes, we can. The question is, can we do 3D array of atoms? Yes. The challenge is, so with 2D, we enjoy this, kind of basically new perfect parallelism in terms of preparation and readout. If we have a, fully 3D array, just from the way how we kind of read out the qubits, we'll have to pay a little bit of a price because we would not be able to read out all layers at once. So, but for example, quasi 3D, is something we can do. Also with this moving architecture, basically dimensionality doesn't matter. We can make any dimensions.
You mentioned that at the boundary, you may have a degeneracy which create a qubits. I wonder whether there's some experimental way to probe or measure those nearly degenerate states when the system have a boundaries.
Yeah, so the question is, basically depending, kind of you can encode qubits basically on the boundaries. And the question is, can we kind of probe this? I believe the answer is yes, Moreover, there are different types of boundaries you can create here, E and M, and actually we have a way to control it. We've done a little bit of work already, but this is definitely something we can do. And I'm happy to discuss it. Yeah.
One more question.
You mentioned adiabatic preparation. What was the reason for that?
So the adiabatic preparation is because you would like to stay in the ground state or close to the ground state, right? Because eventually you want to create a state which is, which is lowest energy, because that's the state we're looking for. And to do it most efficiently, it turns out, there are different ways to do it, but to do it in a many-body system, in particular, in a state that you do not necessarily know what it is, adiabatic, going slow, staying in the ground state is the best way.
Thank you.
Okay, I think better go on to the next talk. Jiewing Wang from Microsoft Research, who again, I think known to all of us.
Thank you, Misha, for an exciting talk.
What? Thank you, Arthur. Thank you. Walter.